Soft continuum manipulators, like this one, are lightweight, cheap to make, and have inherent compliance, which makes them safe for human interaction. However, they are difficult to control because they exhibit infinite degrees of freedom, nonlinear material properties, and large deformations under loading, as shown here. In this work, we present a data-driven approach to identifying soft manipulator models that enables consistent control under variable loading conditions. This is achieved by incorporating loads into a linear Koopman operator model as states and estimating their values online via an observer within the control loop. To do this, we begin by measuring the response of the system under random control inputs for a variety of different payloads. We then use that data to identify a matrix approximation of the Koopman operator, which provides a linear description of the dynamic behavior of the system under various loads. This model is used to construct a closed-loop model predictive controller that enables the robot to follow a 3D trajectory with its end effector. This controller is referred to by the acronym KLMPC. Here, the end effector follows a reference trajectory while carrying a 175-gram payload, achieving a root mean squared tracking error of less than 2 centimeters. For comparison, two other controllers based on models that do not explicitly account for loading are evaluated on this task. We superimpose trajectories for several payloads. It can be seen that our KLMPC controller is far more accurate than the controller shown on the left, and more precise than the controller shown in the middle. By incorporating loads into the Koopman model as states, our approach also enables online load estimation. As the manipulator moves around, an observer infers the most likely value of the payload, given the model and past input-output measurements. Over time, this estimate approaches the true payload value. By combining the estimation and control into a single algorithm, it is also possible to improve control accuracy under unknown loading conditions. Here, as the controller attempts to follow a circular trajectory, the load estimate gradually becomes more accurate and the tracking error is reduced. As a final demonstration, we use the same algorithm to perform the pick-and-place task of automatically sorting objects by their mass. First, a human places an object of unknown mass into the robot's gripper. Next, the manipulator attempts to follow a reference trajectory while estimating the payload. After 15 seconds, the robot moves the object toward the cup that corresponds to the estimated mass of the load and deposits it there. This process is repeated to sort a set of 5 objects. And is shown to work for another set of objects as well. While so far our approach has only been applied to this robot, we believe that our work lays a foundation towards enabling the widespread use of automated soft manipulators in real-world applications.